Have you ever looked up on a clear night and felt the sudden, profound realization that we are but a pale speck in an unfathomably vast, dark sea? And then, inevitably, ask the most ancient and persistent question: are we alone? This fundamental inquiry has echoed through human history, from the flickering light of the first campfires to the piercing gaze of our most powerful telescopes. Today, we embark on an intellectual journey to explore the full narrative of this question: how humanity has posed it, how science has begun to unravel its mysteries, and where the quest for extraterrestrial life might lead us next. This is the comprehensive history of the search for alien life. Our exploration will traverse millennia, beginning with the ancient worldviews where gods, omens, and celestial beings shaped human understanding of the cosmos. We will then witness the dawn of scientific speculation, marked by figures like Galileo, the intriguing misinterpretations of Percival Lowell, and the foundational framework of the Drake equation. Our path continues into the modern era with the birth of Radio SETI, iconic moments such as the enigmatic "wow" signal, and humanity's first deliberate attempts to communicate across the void through missions like Pioneer and Voyager. We will delve into the persistent phenomenon of UFO reports and the subsequent government investigations, before charting the revolutionary impact of the exoplanet discoveries that fundamentally reshaped our cosmic perspective. Finally, we will examine the cutting-edge tools of today: advanced telescopes, sophisticated spectrometers, and artificial intelligence, all meticulously searching for the subtle chemical fingerprints of life, known as biosignatures. We conclude by reflecting on what remains unknown and why the answer to this grand question holds such profound significance for our species. Are you ready to embark on this cosmic odyssey? Let us begin. Long before the advent of radio dishes or space probes, human civilizations intricately wove the celestial sphere into their foundational myths and daily lives. The Babylonians, for instance, meticulously cataloged omens in texts like the Enuma Anu Enlil, interpreting planetary motions as divine messages intended for kings and empires. This practice wasn't merely superstition, it was an early attempt to find order and meaning in the seemingly chaotic heavens. In ancient Egypt, the brilliant star Sirius held immense significance, its heliacal rise signaling the annual, life-giving flood of the Nile. This celestial event marked the beginning of their year, inextricably linking stellar patterns to cycles of life and death, and to powerful deities such as Isis and Osiris. The sky was a living tapestry reflecting earthly existence. Similarly, the Maya developed incredibly precise astronomical tables for Venus, connecting its complex cycles to elaborate rituals and the legitimacy of their rulers. Across the globe, indigenous peoples, from the Aboriginal Australians with their intricate star maps, guiding seasonal knowledge and navigation, to Polynesian navigators who sailed vast oceans by the stars, and Native American tribes whose cosmologies were deeply intertwined with celestial observations, all integrated the cosmos into their cultural fabric. These ancient cosmologies frequently featured beings descending from the sky: gods, spirits, or enlightened teachers. Thinkers and priests utilized celestial events not only to guide agricultural cycles, but also to legitimize political power and to explain catastrophic occurrences. These were not primitive guesses, but sophisticated human strategies to anchor terrestrial life within a larger cosmic order. The question they implicitly asked, though framed in their own cultural language, mirrors our modern inquiry. Is there intelligence or meaning beyond the human realm? They sought answers through rich narrative, ritualistic practice, and, crucially, through diligent and careful observation of the night sky. There are also intriguing ethnographic debates that highlight the complexity of ancient knowledge. The Dogon people of Mali, for example, have been controversially credited with possessing detailed knowledge of Sirius B, a faint companion star invisible without modern telescopes. Scholars vigorously debate whether the Dogon's knowledge is genuinely ancient, passed down through generations, or if it was introduced following contact with Western observers. This very controversy illuminates a crucial point. Humans have long been willing to imbue the skies with profound meaning, and cultural transmission can convey astronomical knowledge in remarkably intricate ways, blurring the lines between myth and observation. The enduring mystery of the Dogon's knowledge serves as a thought-provoking reminder of how much we still have to learn about humanity's ancient relationship with the cosmos. The scientific approach to the question of life beyond Earth began to emerge with the invention of better instruments and a burgeoning willingness to ask fundamentally new questions. Galileo Galilei's telescopic observations in the early 1600s delivered a profound shock to the prevailing geocentric and perfect sphere model of the heavens. He revealed that the moon was not a smooth, pristine orb, but a rugged world of mountains and craters, and that Jupiter possessed its own retinue of orbiting moons. These discoveries suggested that other celestial bodies were, in many ways, analogous to our own Earth. If other worlds shared physical characteristics with ours, then, some daringly argued, perhaps life could also exist upon them. By the 18th and 19th centuries, the concept of a plurality of worlds had become a widely accepted idea among educated Europeans. Philosophers, writers, and scientists engaged in lively debates about the possibility of life on the Moon, on Mars, and on other planets within our solar system. This intellectual ferment laid the groundwork for more focused inquiry. In the late 19th and early 20th centuries, American astronomer Percival Lowell became a prominent figure, popularizing the sensational idea that linear features observed on Mars were, in fact, artificial canals, evidence of a vast intelligent engineering project by a Martian civilization. While we now understand that these canals were optical illusions and observational artifacts, the episode was nonetheless crucial for capturing the public imagination. It normalized the radical notion that extraterrestrial intelligence might not only exist, but could also be discoverable, even visible, through our telescopes. Lowell's work, though flawed, ignited a widespread fascination with Mars and the possibility of its inhabitants, demonstrating humanity's deep-seated desire for cosmic companionship. The true pivot toward an empirical, systematic search for extraterrestrial intelligence occurred in the mid-20th century. In 1961, astrophysicist Frank Drake formalized the problem with his now famous Drake equation. This equation is not a predictive tool, but rather a simple multiplication of several astrophysical and biological factors that, when estimated, provide a framework for calculating the potential number of communicative civilizations in our galaxy. The equation asks us to consider: how many stars exist? What fraction of those stars have planets? How many of those planets are habitable? How often does life arise on habitable planets? How often does intelligent life evolve? And how often does such intelligence develop detectable technology? The Drake equation fundamentally reframed the question of alien life, transforming it from a matter of folklore and philosophical musing into a quantifiable problem expressed in the precise language of science. It provided a roadmap for future research, highlighting the specific areas where our knowledge was lacking and where scientific investigation could yield meaningful progress. Modern SETI, the search for extraterrestrial intelligence, was born from the advent of radio astronomy. In 1960, Frank Drake, the architect of the Drake equation, conducted Project Ozma. He meticulously pointed a radio telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, listening intently for narrow-band radio signals, the kind of artificial carriers that human engineers use for communication. While he detected nothing conclusive, the fundamental methodology was established. Listen for highly structured, narrow-band signals that are rarely, if ever, produced by natural astrophysical processes. This was a deliberate shift from passive observation to active listening for signs of technology. Over the subsequent decades, radio searches proliferated, growing in scope and sophistication. A landmark moment occurred in 1974 when the Arecibo message, a powerful radio broadcast containing simple encoded information about humanity, our solar system, and our biochemistry, was beamed towards the globular cluster M13. This was, in essence, an intentional greeting, a data-richer analog to waving across the vast gulf of space, a deliberate attempt to initiate contact. The message, though unlikely to reach its destination for tens of thousands of years, represented a profound statement of intent. Beyond intentional broadcasts, humanity also launched deliberate artifacts into the cosmos. Between 1972 and 1977, NASA launched the Pioneer probes and the twin Voyager spacecraft. Each carried a symbolic message intended for any future finders. The Pioneer probes bore simple plaques depicting human figures and a map of our sun's position relative to pulsars. The Voyager spacecraft carried the more elaborate Golden Record, a meticulously curated collection of images, sounds, and music from Earth, assembled by a team led by the visionary Carl Sagan. These phonograph-like discs were designed to convey the diversity of life and culture on our planet. These probes continue their silent journeys outward, tiny human emissaries venturing into the interstellar void, carrying our story to the stars. And then, tantalizingly, came the anomalies. On August 15, 1977, the Big Ear Radio Telescope at Ohio State University recorded an exceptionally strong, narrow-band signal of unknown origin. Jerry Eman, a volunteer examining the printout, circled the data and famously scrawled "Wow" next to it, a spontaneous expression of astonishment. This singular event, now known as the "Wow" signal, lasted for 72 seconds and has never been repeated or definitively explained. While various natural explanations have been proposed, none have been conclusively proven. The "Wow" signal remains an iconic maybe, a powerful provocation that continues to fuel the search and keeps the question of extraterrestrial intelligence vibrantly alive in the public consciousness. It serves as a potent reminder of the unexpected possibilities that await. Subsequent decades saw the launch of even more sophisticated projects. SETI Home, initiated in the 1990s, harnessed the distributed computing power of millions of home computers to analyze vast amounts of radio data, democratizing the search. More recently, Breakthrough Listen, launched in 2015 with significant private funding, has brought unprecedented resources and modern computing capabilities to bear on the sky. Through all these endeavors, the core method has remained consistent: patiently scan, listen, analyze, and rigorously verify any potential signals. The search is a testament to human perseverance and scientific rigor in the face of immense cosmic silence. Running parallel to the systematic scientific searches for extraterrestrial intelligence are the persistent reports of unexplained aerial phenomena, what the public commonly refers to as UFOs, and more recently, UAPs, unidentified aerial phenomena. While a vast majority of these sightings ultimately receive prosaic explanations, misidentified aircraft, weather balloons, atmospheric optical effects, or even simple lens flares and misidentified astronomical bodies, a persistent residue of reports continues to defy straightforward, conventional explanations. These unexplained cases fuel public fascination and speculation. Governments, particularly in the United States, have at various times taken such reports seriously, albeit often with a focus on national security rather than extraterrestrial contact. Project Blue Book, a U.S. Air Force study conducted from 1947 to 1969, systematically collected and investigated thousands of UFO reports. While the project concluded that most cases could be attributed to mundane sources, a small but significant fraction remained officially unidentified, contributing to the enduring mystery. These unexplained cases, though few, kept the public's imagination alight. In recent years, interest in UAPs has resurfaced dramatically, driven by official disclosures. The Pentagon declassified and publicly released several videos captured by U.S. Navy pilots, showing anomalous aerial objects exhibiting unusual flight characteristics. These videos, often accompanied by pilot testimony, sparked renewed public and congressional attention. In 2022, the U.S. government established the All-Domain Anomaly Resolution Office, BARRO, with the mandate to coordinate investigations into such incidents across all branches of the military and intelligence community. This move signaled a more formalized approach to understanding these phenomena. It is crucial to emphasize that government interest in UAPs does not automatically imply an extraterrestrial origin. Primarily, it signifies a desire to understand phenomena that are currently unexplained, to ensure they do not represent unknown foreign technology or pose a safety risk to military operations. The cultural effect of these reports and investigations has been immense. Public fascination with UFOs drives significant media attention and, in turn, can exert political pressure. This societal interest can influence funding priorities for scientific research and shape the broader scientific attention given to the search for life beyond Earth. The UFO-UAP narrative is an integral part of the societal history of this search, a complex interplay of human perception, anecdotal evidence, institutional response, and enduring mystery. It highlights how deeply ingrained the question of, "Are we alone?" is within our collective consciousness. For centuries, and indeed until the 1990s, the existence of planetary systems beyond our own solar system remained purely hypothetical, a subject of theoretical speculation. Then, everything changed. In 1992, astronomers Alexander Volshan and Dale Frail made a groundbreaking discovery: planets orbiting a pulsar, a rapidly rotating neutron star. While these were exotic worlds, orbiting a dead star, their discovery provided the first irrefutable proof that planets indeed exist around other stars. This was a monumental step, confirming that our solar system was not unique in possessing planets. The true revolution, however, began in 1995, when Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, the first planet confirmed to orbit a Sun-like star. This discovery was a paradigm shift, immediately implying that planets are not rare cosmic anomalies, but are likely common throughout the galaxy. The implications for the search for life were enormous, transforming the theoretical into the tangible. The Kepler Space Telescope, launched by NASA in 2009, fundamentally reshaped our understanding of planetary abundance. Kepler meticulously observed a single patch of sky for years, detecting exoplanets by observing tiny, periodic dips in the brightness of stars as planets transited, or passed in front of, their host stars. Kepler's census revealed thousands of planet candidates and definitively proved that small, rocky planets, the kind most likely to be habitable, are not rare but are in fact incredibly common. Today, based on Kepler's data and subsequent missions, we know that our galaxy teems with planets, billions, by conservative statistical inference. This abundance shifted the focus of the search from "do planets exist?" to the far more nuanced questions of which planets are habitable, and which possess atmospheres and chemical compositions that we can detect and analyze for signs of life. Subsequent missions, such as TESS, Transiting Exoplanet Survey Satellite, have refined the target list by identifying planets orbiting nearby, bright stars, making them ideal candidates for detailed follow-up observations. The next crucial step involves using spectroscopy to study the atmospheres of these exoplanets. The James Webb Space Telescope, JWST, a marvel of engineering and scientific ingenuity, has, in its early operational years, already begun to measure atmospheric components on distant exoplanets. It has detected water vapor, carbon-bearing molecules, and even evidence of clouds. These groundbreaking detections demonstrate that atmospheric characterization, the meticulous search for potential biosignatures like oxygen, methane, or specific chemical disequilibria in gas mixtures that could indicate biological activity, is not only possible but is now actively underway. For the very first time in human history, we can move beyond merely counting planets and begin the arduous but exhilarating task of testing for life's chemical fingerprints across the galaxy. This represents a profound paradigm shift in the search for life beyond Earth, moving us from speculation to empirical investigation. Today's search for extraterrestrial life is a multi-pronged, highly sophisticated, and inherently multidisciplinary endeavor. Radio SETI continues its vital work, patiently listening for the telltale techno-signatures of intelligent civilizations. Complementing this, optical SETI actively searches for bright, pulsed laser signals, which could be another form of interstellar communication. Beyond direct communication, researchers are also conducting broader surveys for other techno-signatures, large-scale energy patterns, industrial pollution, or waste heat that an advanced civilization might inadvertently produce. These are subtle clues that could reveal the presence of technology on a cosmic scale. Astrobiology, a rapidly growing field, plays a crucial role by studying life in Earth's most extreme environments, from deep-sea hydrothermal vents to arid deserts and polar ice caps. This research helps us understand the astonishing resilience and adaptability of life, pushing the boundaries of what we consider habitable and expanding our conceptual framework for where life might exist elsewhere. Simultaneously, planetary science missions are actively searching for microbial life much closer to home. Mars rovers meticulously sample ancient lake beds and subsurface environments for signs of past or present life. Future missions are planned for icy moons like Europa and Enceladus, which are believed to harbor vast subsurface oceans. These missions aim to study their geysers and plumes for organic molecules and potential biosignatures. Other probes are being designed to return samples from promising locations, bringing extraterrestrial material back to Earth for detailed analysis. On the analysis side, the sheer volume of data generated by these missions and telescopes necessitates advanced techniques. Data science and machine learning algorithms are now indispensable tools, sifting through massive datasets to identify subtle anomalies that might otherwise be missed. The detection problem is inherently statistical and demands rigorous verification. Any claimed detection must be reproducible, unequivocally distinguishable from terrestrial interference, and thoroughly parsed to rule out all plausible natural causes. This meticulous process ensures scientific integrity. Beyond the technical aspects, there is a crucial social and procedural dimension to the search. The scientific community has engaged in extensive debates about how to respond to a confirmed detection of extraterrestrial life, particularly intelligent life. Organizations such as the International Academy of Astronautics have outlined post-detection protocols that provide guidelines for the verification of a signal and for the responsible dissemination of results to the public. The overarching goal is to avoid premature or sensational claims, to ensure rigorous scientific verification, and to prepare humanity for the profound social, ethical, and philosophical consequences of such a monumental discovery. The point is not to establish a rigid playbook, but rather to ensure that science remains careful, credible, and prepared, whatever the future may hold. So, after centuries of speculation and decades of systematic searching, where does that leave us? We have learned an immense amount about our place in the cosmos. We now know, with scientific certainty, that planets are incredibly abundant throughout the galaxy. We understand that the fundamental chemistry necessary for life, carbon, hydrogen, oxygen, nitrogen, and other elements, is widespread across the universe. We have also discovered that nature produces astonishing complexity under a vast range of conditions, from the simplest microbes to the most intricate ecosystems on Earth. We have sent our messages into the void and listened patiently for a reply. We have amassed a collection of tantalizing anomalies, signals like the enigmatic WOW, unexplained aerial incidents, and intriguing atmospheric hints on distant exoplanets that continue to prompt scientific debate and public fascination. However, despite all these advancements and efforts, what we have not yet achieved is a confirmed, unambiguous detection of life beyond Earth, neither microbial nor technological. No repeated verified narrowband signal has been authenticated as artificial in origin. No atmospheric spectrum from an exoplanet has yet produced an unambiguous, irrefutable biosignature that cannot be explained by abiotic processes. And no government release, despite recent disclosures, has presented evidence that compellingly and definitively demonstrates an extraterrestrial origin for any observed phenomenon. This absence of a definitive detection is not, however, a failure of the search. On the contrary, it represents a crucial scientific milestone. The question of life beyond Earth is no longer merely a philosophical inquiry. It has become a concrete, empirical problem. We now possess the knowledge of what to look for. We have developed increasingly sophisticated tools to seek it, and each null result, each non-detection, serves to narrow down our hypotheses and refine our search strategies. This systematic process of elimination and refinement is precisely how science progresses, moving us closer to the truth, one observation at a time. The future of the search for alien life promises even more sensitive telescopes, more powerful arrays, and increasingly coordinated multidisciplinary searches. The James Webb Space Telescope will continue to refine its atmospheric studies of exoplanets, pushing the boundaries of what we can detect. Next-generation ground-based telescopes, such as the Extremely Large Telescope, the 30-meter telescope, and the Giant Magellan Telescope, will possess the unprecedented capability to directly image Earth-like planets around nearby stars, potentially revealing their surfaces and atmospheres in exquisite detail. Projects like Breakthrough Listen will continue to expand their bandwidth and sensitivity, scanning the skies with unparalleled precision. Beyond these large-scale observatories, private and public ventures may soon mount dedicated life-hunting missions to the most promising targets within our own solar system, such as the subsurface oceans of icy moons like Europa and Enceladus, or even to nearby exoplanets if technology allows. The possibilities are vast and exciting. However, the road ahead also presents profound risks and philosophical puzzles. A confirmed detection of extraterrestrial life, particularly intelligent life, would fundamentally reshape human self-understanding and our place in the cosmos. It would raise a myriad of ethical, legal, and cultural questions that we have only just begun to imagine. How would humanity react? What would be the implications for religion, philosophy, and our sense of uniqueness? That is precisely why scientists, ethicists, and policymakers are actively engaging in these discussions now, to prepare for a discovery that, depending on one's optimism, could be either far away or just around the corner. The journey continues, and the implications are staggering. So, are we alone in this vast, silent cosmos? We still don't know for certain, but this is a truly unique moment in human history. The first time humanity has possessed both the sophisticated instruments and the rigorous scientific methods to begin answering a question that has captivated us for as long as we have gazed up at the stars. The search is no longer confined to myth or speculation. It is a vibrant, empirical scientific endeavor. If you want a deeper dive into any specific chapter of this incredible story, whether it's the enduring mystery of the WOW signal, the profound message carried by the Voyager Golden Record, the revolutionary discoveries of the Kepler mission, or the cutting-edge techniques JWST employs to search for life, tell me which one, and I'll create a dedicated episode just for you. Like this video, subscribe to our channel for more cosmic explorations, and join the conversation in the comments below. The search continues, and perhaps, just perhaps, the sky is listening.